Okay, so time variation, we consider matrices and vectors to be time varying, and we consider most properties to be pointwise in time. And if the property exists for the time varying matrix, then it will exist for all time. Okay. Let's now talk about matrix calculus. Just a quick review of matrix calculus. So integrals for a of t, or time varying a, that is a matrix. Okay, so if we want to integrate a matrix from 0 to infinity a of t with respect to t, then we are talking about, the integration of each element of that matrix from 0 to infinity a11 of t with respect to t, integration from 0 to infinity a12 of t with respect to t, and so on. And this is the integration of from 0 to infinity of a21 of t with respect to t, okay, and so on. So integration of a matrix is equivalent to the integration of each element of that matrix. Derivative is also a similar thing. So when we talk about derivative, so if you differentiate a matrix with respect of time, then we talk about differentiation of each element of that matrix. So this is equivalent to the differentiation with respect of time a1 of each element. So a11, the derivative of a12 with respect of time, and so on. This is d over dt, a21 of t. Okay. Also, other properties also hold. So for example, the product rule. So the product rule, so let's say that we want to differentiate with respect of time, d over dt, at b of t. So these are two matrices, time varying matrices, and we would like to differentiate them with respect to time. So this is equal to a dot, where a dot means the derivative of a with respect to time. So a dot times b of t plus a of t times b dot of t. Okay. Now, can I say that this is equal to 2a of t, a dot of t, if b of t is equal to a of t? Anybody? Can I say that? if b of t is equal to a of t, then can I say that this is equal to 2a dot, which also leads to, so this leads to d a squared of t dt squared, no, dt, sorry, d a squared of t over dt is equal to 2a of t a dot of t. Is that possible?
No, because a dot a is not equal to a dot.
Exactly. Thank you. That's exactly, this is correct. So this is not possible because a and a dot, they do not commute. Okay. So you have to be really, really careful when dealing with matrices, all right? So this is not possible because A dot is not equal to A dot A. Not necessarily equal to. Okay, so this is not possible. All right. Another very useful result is the fundamental theorem of calculus. So the fundamental theorem of calculus says that when you differentiate an integral, so when you differentiate d over dt, the integral from 0 to t, and this is the key, from 0 to t, where the variable here is t, b of sigma with respect to sigma, okay? Then that will be b of t, okay? It's the inverse of the integral is the derivative, you can say that, okay? As long as there is this common here, which is this upper limit, that is the time that we are differentiating with respect to, so time. So this is the fundamental theorem of calculus. Okay, there is another result. It's called Leibniz rule. So Leibniz rule says that the derivative of this integral from f of t, so when you have the limits of the integration to be functions of time, okay? So the derivative of this b, t, and sigma with respect to sigma. So here, notice the difference between this one and that one. This one, the limits of integration are functions of time, nonlinear functions of time. This is a function of time and sigma, which is the dummy variable that I'm integrating with respect to, okay? So Leibniz theorem says that the derivative of this integration is equal to b t g of t g dot of t minus b of t f of t f dot of t plus the integration from f of t to g of t d over dt b t and sigma with respect to sigma. So let's take an example just to show the application of this Leibniz rule. So example. We want to differentiate from 0 to t. Okay, in this case here, the bounds of the integral are linear. A of x, a of sigma, integration from 0 to sigma, a of gamma with respect to gamma. So this with respect to sigma. Okay. So as you can see here, this is a rather complex integration. It involves two integrations from 0 to t and from 0 to sigma. First one is a of sigma. So this integration is for the whole thing here, and this integration for a. So it's a double integration. We would like to take the differentiation of that. So if we call the whole thing this one, the whole thing this as b of t and sigma, okay, and also we notice that f of t is equal to 0, right? And g of t is equal to t. So this is equal to applying now Leibniz theorem, okay? So b is what's inside. So that's a of t. That's bt and gt, where gt is t. Okay, so now I'm substituting by sigma by g of t here. Here, so this is a of t, and from 0 to t, a of gamma with respect to gamma, right? This times 1 because this is g dot, okay? And then minus, so I'm continuing now, minus a of 0, integration from 0 to 0. So now I'm doing this one here. So now b, t, and ft, I'm doing this minus b, t, and ft, f dot t. Ft is equal to 0. So that's why I have a0, integration from 0 to 0, a of gamma, d gamma, times 0, because this is f dot. All right. And as you can see, integration from 0 to 0 is nothing but 0. Okay. Plus the last one, the last part of the integration, which is from ft to gt, differentiation of b. So that's from 0 to t, d over dt, differentiation of b, t, and sigma. So I need to substitute back by sigma. So that's sigma, integration from 0 to sigma, a of gamma with respect to gamma. Okay, the whole thing with respect to sigma. Okay, anybody can tell me what's the result of this term? What's the end result of this term here?
It's a of sigma square.
Any other try? No, that's not good. Yes, go ahead.
It's I think it's so it's a differentiation of a of sigma square. So it's 2 sigma, 2 a of sigma.
No, that's not true.
Product rule, product rule.
No.
There's
not
T, so
It's B.
correct.
What's that?
Isn't it 0?
It's
There's
B.
no dependence on 0 on T in the inner brackets.
Correct, Dennis. Good job. It's 0 because we are differentiating something with respect to time, and there is no time in this here. So the whole thing here is 0. All right. So the end result is A. So the end result is the first term here. Okay. And that is A of t from 0 to t, a gamma with respect to gamma. Okay, so as you can see, we have simplified a differentiation of double integration into this, which is considerably simpler than, of course, this one here. All right. Let's continue. So, fact. The norm of an integration from T0 to T, x of sigma with respect to sigma, okay, is less than or equal to the integration from T0 to T. So the norm goes inside, but if the norm goes inside, then we'll have less than or equal to. So less than or equal to x of sigma with respect, with respect to sigma. Okay, so an explanation of this fact comes from the triangle inequality. So this comes from triangle from the triangle inequality, right? Which says that in the case of the scalar, in the case of the scalar matrices or vectors, the magnitude of A plus B is less than or equal to the magnitude of A plus magnitude of B. And you can see, you can recognize that integration is nothing but summation, right? So you are summing a lot of things. So it's the same thing as in here. And then this is less than or equal to the sum of the magnitudes of the individual elements. All right. So this is a quick fact. Let's continue. So for example, there is an exercise in the book, which is exercise 1.18. It says that for x time varying, right? That's a vector, and also continuously differentiable. So continuously differentiable here means that x, I can differentiate x, that will give me x dot. I can also differentiate x dot, that will give me x double dot, right? Which is d x, d squared x over dt squared. And then I can differentiate that to x triple dot and so on. Okay, so it's a continuously differentiable to as long as I want. This is what this means. Okay, so if x is continuously differentiable, okay, and by the way, continuously differentiable implies continuity, and sometimes we call it smooth. So if I have a vector or I have a signal that is smooth, it implies continuous differentiability. Then the magnitude of d over dt of the norm x of t, okay, is less than or equal to the norm of the derivative. So the magnitude of the derivative of the norm is less than or equal to the norm of the derivative x of t. Take a second here to look at this. The magnitude of the derivative of the norm is less than or equal to the norm of the derivative of the vector. Let's prove that. Maybe it's not easy to see how that comes, the intuition behind this, but let's see the proof of that. So let's look at first at the derivative of the norm squared. Okay, we know that the derivative of the norm squared is the magnitude of what's inside, which is what? Which is 2 times x of, by the way, this is x of t. Okay, so I'm gonna write it here. Because if this is not x of t, not time varying, then of course the derivative of that is going to be 0, right? Times d over dt, the norm of x of t. Okay, so it's the product rule. And notice that I am able to do this, right? Why am I able to do this? Because the norm is a scalar. Whenever we take the norm or the magnitude of anything, we are talking about a scalar entity here. Okay, so now I can take the 2 outside and I can do this. So this, and also I can say that this is x of t, and also times the magnitude of d over dt x of t. Okay, so I can go from here to here because yeah, they are so this is because it's positive, so I can take it outside. This is positive, I can take it outside, and I will be left with this one. I can also do the same here in a slightly different way for the benefit of everybody. So the magnitude of d over dt, norm of x squared, okay, that is equal to the magnitude of what? D over dt. What is the definition of the norm of x squared? That's the 2 norm. We did that last lecture. It's nothing but x transpose of t, and actually we did it at the beginning of this lecture. X transpose t, x of t. Okay. So this is just the definition of the norm squared. So applying the product rule, the chain rule, then you will have x dot transpose of t times x of t plus x transpose of t x dot of t. Okay. Now, you need to note that x dot of transpose of t x t, if you transpose that, okay, this is x dot is the same as x transpose t x t, which is the same as x transpose t x dot of t. Why? Because x transpose of t x of t is a scalar. Okay, so the product of these two is a scalar. So I can, if I take the transpose of a scalar, it doesn't matter the order. Okay, so I can flip the order. So this is just the same as this is just another way of showing this. Okay. So so this is just a side note here. Okay. So going back now to this one here. So if we go back to this, then so this implies that d over dt x squared, I'm omitting the t here just for convenience, but there should be a t. This depends on t. Okay. So this is equal to the magnitude of d over dt x transpose of t x of t, which is the same as, we just showed that, 2x transpose of t x of t x dot of t, sorry. Okay, and this is what? This using the properties of matrices and vectors. This is equal to 2, the norm of x of t times the norm of x dot of t. Can you see that? Can you all see that? Why? Because
That is Cauchy-Schwarz, right?
thank you. That's Cauchy-Schwarz. That's Cauchy-Schwarz. Absolutely right. You are absolutely right. Right? With one slight subtle notice here, I mean, which is Cauchy-Schwarz will give you this less than or equal to 2 norm of x transpose of t norm of x dot, right? And of course, the norm of x transpose is the same as norm of x. Okay, so you get that. Okay, so 6. So we have d over dt x of t squared is equal to so from before we know that this is equal to 2 norm of x magnitude of the derivative. So let's write that. Okay. We also know, we just showed this. Okay. And the magnitude of d over dt x of t norm is less than or equal to 2 norm of x of t norm of x dot of t. Okay, so we have these two now. Okay, now you can compare these two together. So what's going to happen if you compare this? This is an equality and this is an inequality. Okay, so that means that this one is less than or equal to that one. Okay, so this implies that 2x of t magnitude of d over dt norm of x of t, right, less than or equal to 2 norm of x of t x dot of t, right? So now I can, because these two are positive, so I can divide, no problem. Also, I have a norm of x here and a norm of x here. I can get rid of that with the assumption, very important here, I can also do that, right? But here, only for x of t is not equal to 0. I can, otherwise I cannot divide by x of t, okay? So, so that means the magnitude of d over dt of the norm x of t, okay, is less than or equal to the magnitude of the derivative of x. Okay, and that's what I want to show. All right, any question? Okay, let's take a minute here. Okay, so this concludes our discussion of matrix algebra and the norms and all that. Okay. Now I'd like to start discussing linear systems equations or models of linear systems. So this is basically chapter 2 of the book, which is linear systems equation. So in general, as we discussed in the first lecture, one of the equations that can describe a linear system is the state space equation, right? Which is of this form here. So x dot of t is equal to a of t, x of t plus b of t, u of t, and the output y of t is equal to c of t, x of t plus d of t, u of t. This is known as linear time varying system. Linear because the function here changes linearly. So if this is the y-axis, this is the x-axis, then as you can see, this A matrix is a linear matrix, represents a linear relationship between f of, so if I call this f of t or f of x, sorry, and this is x, so these two are related through this A matrix, and also B is also a matrix, which is a linear function. So, the relationship between the left-hand side and the right-hand side, the connection between the left-hand side and the right-hand side is a linear. So that's why we have a linear system. But of course, this is not rigorous. If you want to make sure that the system is linear or not, you need to apply the definition of linearity. Anyway, also the system is time varying because the matrices A, B, C, and T change over time. Okay, obviously X is going to change over time because this is a dynamic system, right? This is not a static system. So that's, we don't consider that, it's a given. So, but what makes this model time varying is the fact that the matrices A, B, C, and D change with time. So X, so we're talking about X of t as a vector. We talk about U, which is typically we consider U as the control input or input to the system. Also a vector of a dimension M. So we have M number of inputs. Y of t, we consider that the output, and here we assume it to be of dimension P. So we have P number of outputs. So this is a multi-input, multi-output system where we have M number of inputs, P number of outputs, and N number of states. X is the state of the system. And in general, we call this system an n-dimensional system. An n-dimensional system because I have n number of differential equations based on the dimension of X. So this is a state. This is input. And this is output. Okay. Also, I can talk about the matrices A of t, of course. Now the matrix, because this is n-dimensional, so this has to be n by n. B, the dimension of B matrix has to be n by m. And the dimension of C of t has to be dimension P by n. And D of t has to be dimension P by m. Okay. So, and also the initial conditions. So xt0, I'm gonna call it just x0. This is the initial condition of the system. Okay, and also I'm going to assume that t is larger than or equal to t0. Okay, so this is one thing. And also I can talk about a transfer function of the system. Like what we did before. So I have g that links y of t with u of t. So y of s, so I can now take the Laplace of this, I get y of s over u, capital U of s is equal to, for example, just here s squared plus 3s plus 2, for example. This is for example. Of course, I can go from here to here, as you will see in a minute. You can go from here to here by assuming that the initial conditions are 0. And this is a typical, this is the way to do it when you go from differential equation form of the system to the transfer function form. Okay, so let's continue with this. So let's say, so I'm still with this one here. So this is the transfer function form. Okay, I can go from the differential form to the transfer function form by taking the Laplace and assuming the initial conditions are equal to 0. I also can go from this form to the differential equation form, right? If you cross multiply, okay, so cross multiply this. If you cross multiply this, what will you get? And take the inverse Laplace. So cross multiply. I'm going to call this 1. And take the Laplace inverse. Okay, that would lead to y dot dot, which is the double derivative of y of t plus, because s squared y is the, if you take the Laplace derivative, inverse Laplace derivative, inverse Laplace of that, that would be y dot dot plus 3 y dot, okay, plus 2y is equal to u of t. Okay, now so I want to go from here to here. This is my goal here. Okay, I'm going to go from state space to transfer function. So how can I do that? How can I go now from here to the state space representation, to this representation of the system? I'm here now. Anybody, there is something that I can do to go to that form. Anybody? Can anybody help me with that?
Laplace.
What's that?
Laplace.
No. My question is, if I have something like this, okay, and I want to go to the state space representation, how can I do that?
Take x dot to be, or say take x dot to be y dot of t and y double dot of t, or use them as measurements.
You are so close. You are so close to the result, to the answer.
You create two states, right? So x is y, x dot is y dot,
Yes.
and then that's state space. You can take the derivative of that, which will get you your state equation.
Exactly, Dennis. So this is a typical trick we do to convert an n-dimensional differential equation to n number of first order differential equations. And that trick is the following. This is a very important procedure that always is done to convert a differential equation to a state space equation. Remember, the state space equation is nothing, it's also a differential equation, but the distinctive feature here is that you have n number of first order differential equations. Okay, so define x1 to be equal to y, to be equal to the state, okay? And x2 to be the derivative of this, x1 dot, which is equal to y dot, right? So using this derivative, you have, that means x1 dot is equal to what? To equal to y dot, right? So this is one, and x2 dot is equal to x1 dot dot, right? Which is equal to y dot dot, right? And from here, this is equal to minus, so this is y dot dot from here, it's equal to minus 3y dot, and y dot is equal to x2, so minus 3 x2, or let me write it this way, minus y dot, let me write it first like this, so minus y dot minus 2y, I'm omitting the dependence on time for convenience, plus u, okay? So this is equal to minus 3y dot is equal to x2, okay? Minus 2y, which is equal to x1 plus u. All right, so this is x2 dot. So now I have, so this leads to x1 dot is equal to x2, and x2 dot is equal to minus 3x2 minus 2x1 plus u. Okay, so I have two differential equations that are of the first order. There is only one derivative in each equation, and everything else is the states and the input. That's it. Okay, so this is the state space representation. I can represent this in the matrix form. So this is the same as, or in a compact form, x1, x2 equal to 0, 1, minus 2, minus 3, right? Times x1, x2 plus 0, 1, u. So I'm representing these two equations in a matrix form, right? And so this is going to be my A, this is going to be my B matrix, right? And also, suppose you need to define your output, right? So suppose that we measure x1. Okay, so I'm going to define it as y. Then, so now my output is x1. So my output is x1. Okay, so I need now to define y as cx plus du. So if y is equal to x1, that means that c has to be y is equal to c has to be 1 and 0 times x1 x2, right? Because y is equal to x1, so it's that. So this is going to be my c, okay? Plus you have du, okay? You have du, but here this is what we are assuming the output to be. It's not going to depend on the input, which means that d is going to be equal to 0. Okay, and the dimension of d here depends on y and depends on u, because I have only one output and one input, so it's 1 by 1. So this is d. Okay, suppose that y is equal to 2x1 minus x2. All right, instead of y is equal to x1, now I suppose that y is equal to 2x1 minus x2. Well, I can represent this as well as 2 minus 1 times x1, x2. Okay. So this is transfer function to state space. Okay, this is what we have done right now. So starting with a transfer function to state space. Now, let's do state space to transfer function. So notice something here. Notice that when we talk about transfer functions, we talk about time invariant systems. Okay, so when we talk about transfer function, we typically talk about transfer linear systems, time invariant system. At least in this example here. So here we talk about time invariant system, and also what I'm going to consider now next is time invariant systems. So consider x dot of t is equal to a x of t, okay, plus b u of t, and y of t is equal to c x of t plus d u of t. So this is called a linear time invariant system. Okay. So to go from here to transfer function, as I mentioned before, you just take the Laplace transform. So take the Laplace transform. So this is, when I do this, that means this is Laplace transform. I'm applying Laplace transform. So Laplace of x dot of t equal to the Laplace ax of t plus bu of t. Okay, so that means if I take the Laplace of x dot, that's what? That's equal to s x of s. Okay, so here I'm going to just write assume 0 initial conditions. Okay, so if you apply Laplace to that, that would lead to Sx of s, okay, equal to Ax of s plus Bu of s. And if you take the Laplace of y of t, you take the Laplace of the right-hand side, Cx of t plus du of t, okay, which leads to y of s is equal to Cx of s plus du of s. So remember, the transfer function is a relationship between an output and input. So this is what I need to do. Then the nice thing about Laplace is that now I have two equations that are algebraic. So I can manipulate these two equations to find a relationship between y and u, okay? Which means that I need to get rid of this x from this equation here. So to get rid of x, let me get x from the first equation. So from first equation, so this one here, I have Sx of s is equal, minus, take the a as to the other side, minus a x of s is equal to b u of s. Okay, now take x as a common factor. So you have S identity matrix. Remember that these are matrices. So S times the identity matrix minus A, okay? The whole thing multiplied by X of S is equal to B U of S, which means that X of S is equal to B U of S over Si minus A. Is this correct?
No,
Why not?
it's a matrix.
Exactly. So this is not correct. So the correct thing is X of S is equal to, and how about this? B U Si minus A inverse. Is this correct?
Also no.
No, right? Why? Because we are multiplying from the right? We should multiply from the left. So this is equal to multiply both sides by Si minus A inverse from the left. So this is wrong and this is wrong. So Si minus A inverse B U of S. Okay, now take that, substitute it back now into here. Okay, so that means Y of S is equal to C times this Si minus A inverse Bu of S plus Du of S. This is equal to, now take U as a common factor. So you will have C Si minus A inverse B plus D, the whole thing here multiplied by U of S. And that's my transfer function. Right? So this is equal to G of S times U of S. Okay, and notice this is very important. Okay, we're dealing with a matrix form here. So notice that the transfer function here is a matrix transfer function, meaning it has individual, it's a matrix of transfer functions. So I can talk about G11 of S, I can talk about up to G1N, I'm sorry, M number of them, because I have M number of outputs. So 1 of S, okay? And here it goes to up to GP1, because I have P number of inputs, or is it the other way around? No, it's P number of outputs and M number of inputs. Yeah, so it's GP1 of S up to GPM of S. Okay, so it's a matrix of transfer functions. So this transfer function relates the first output with the first input. This second transfer function relates the first output with the second input. The last one here, this transfer function relates the first output with the last or mth number or mth input. Similarly for the other things here. Okay, still have time. Any questions so far? Is there any question?
So if we were to convert this matrix form fully into the, I mean, it's not fully, it's just, we just take a line of it. I mean, like one horizontal row of these, say, coefficients to convert to the single, say, to the, how am I going to describe? To the transfer function we see like few pages ago, which only consists of, which only has one input or one output, those kind. Yeah.
So what's your question again?
So does it, so from few pages ago, we have a transfer function, or say the transfer function few pages ago was 1 over s squared plus 3s plus 2. This such a
Yes.
simple form. So does that mean like when we are doing this, so does that mean when we are, when we reach this matrix form, we just take whichever, so whichever g, oh, I see. So does that mean we just take whichever g to correlate the
No.
output to the input?
No. To answer
No,
your question, no. Okay,
okay.
so you're thinking about this one here.
Yeah.
And we have this one here, okay?
Yeah.
These two are totally different things. This is a
Yes.
single input, single output system, okay? So here I'm assuming, as you can see from here, this represents a single input. So the system has one input and one output. This general form assumes that I have multiple inputs and multiple outputs. If you have a system that has multiple inputs and multiple outputs, I don't want to generalize them. I was going to say you cannot put it in a single input, single output form because I don't know that. But what I'm saying is the representation of multiple input, multiple output, okay, is different. Is different than the representation than a system that has a single input, single output. Do not mix these two things. Okay. So it is given that you are dealing with a system that has multiple input, multiple output system. Okay. So you deal with it that way, which means you cannot say that, oh, I'm going to choose this one or that one to represent the transfer function of the system. No, you need to deal with it as a whole like this one. Okay.
Okay. So it's basically like I mean, so basically this big matrix of transfer function is like a chart. Like if you're going to like to correlate like input 1 to input, say input m, I find 1m transfer function, and that is the one I had to go to. If I had to correlate to input 2 to input 1, I find G21 to correlate that.
That's correct. Yes.
It's like a chart. Okay.
Yes.
I
that's
see.
True. Yes. Okay. So let's continue.
I have a question also.
Absolutely. Go ahead.
Are A, B, C, and D functions of time here?
No. So in these two equations, when I talked about transfer function and state space, I am specializing my discussion to time invariant systems. Okay, so here I'm talking about, yes, I started with the general form, but the discussion, the conversion from transfer function to state space, here I'm considering time invariant systems. Okay.
Okay, thank you.
Yeah, no problem. So guys, I need you to pay attention to what I'm saying whenever we discuss time variant and time invariant. So in this lecture here, I am not saying that whatever we are doing here can or cannot apply to time varying systems. All right. So here I'm just saying that if we take a time invariant system, this is what is going to happen. Okay. So in general, when we talk about time invariant and time varying systems, you have to be careful about applying whatever we do to time invariant systems to time varying systems. In other words, you only apply any tool that we study for, let's say, time invariant, apply it to time varying, only apply it when we consider a theorem, a proven theorem that says, yes, you can apply whatever we did here to time varying systems. Okay? If there is no proof, no theorem that says that, then you have to be really careful. Okay? You had to be really careful and cannot generalize and say, oh, because this applies or works for time invariant system, it's going to work for time varying systems. Okay? It's not always the case. It's not necessarily the case. Okay? So you have to be careful about these, you're talking about two totally different things. time varying and time invariant. Is that clear? Okay. I know sometimes it may be confusing, but you have to separate the two, time varying and time invariant, and be careful. I'm not saying you cannot do or you can do. I'm just saying just be careful when applying tools for one form of models to another.
And Professor, I wanted to talk about
Yeah.
like when you're doing the X dot, can you make the dot a bit larger for clarity?
Absolutely, I will do that. Thank
All
you
right,
for
thank
saying
you.
that. Thank you. Okay, so let's take an example. So let's take a second order system. So you have x1 dot and x2 dot. So this is a state space representation of a system. 0, it's a time invariant. So 0, 1, minus 2, minus 3. X1, x2, plus 0, 1, u. And y is equal to 3, 1, x1, x2. Okay, so now we need to find a transfer function for this system. All right, so compute. Of course, something I haven't talked about enough yet, which is why do we need to model the system in the state space, or model the system in a transfer function, or a model system in a differential equation form? All these forms are equivalent, okay? They are exact, they describe the same thing, okay? But choosing one over the other, choosing one form over the other is actually up to the designer, up to you, okay? Each one may be more convenient to something. So for example, if you put the system in the transfer function form, then you are saying, okay, I don't care about what's going on inside the system. I only care about the relationship between input and output. If you do care about what's happening inside the system, how the internal states are changing, then maybe the state space representation is a good thing for you. If you want to, for example, find the solution or how the states behave over time, then maybe you can, or if you want to model the system from physics, then you'll find yourself dealing with the general form of differential equations. So each one, it depends on the application, it depends on different things, which form you can consider, or you should consider. So, okay, so now compute the transfer function. So we want to find the transfer function of this example here. So compute the transfer function. Okay, so if we want to find the transfer function, I don't need to go over all this. I can go directly to this one here, which is this is my transfer function. C times Si minus A inverse B plus D. Okay, C, B, and D and A are given. Okay, so this is A, this is B, this is C, and D is equal to 0. All right, so that's it. I only need now to compute this. So I will start with Si minus A. Okay, so Si minus A. So Si is S and S, right? So I'm gonna write it just for you guys. So we have SS00, that's Si, minus A, which is 0, 1, minus 2, minus 3. So if you do that, then you will end up with S minus 1, 2, and S plus 3. Okay, and so take the inverse now of that. So we have Si minus A. And by the way, for time invariant systems, MATLAB can also do that. There is a code in MATLAB. It's called SS2 TF that will do the job for you too. But for and you will see that MATLAB can be handy when you are dealing with a system that is high dimensional, right? But for 2-dimensional, as you will see right now, it's straightforward to do it by hand. So SI minus A inverse, which means you need to take the inverse of this one. So that means 1 over the determinant, and the determinant here is S times S plus 3 plus 2, okay, times the adjoint, and the adjoint is S plus, so you swap the diagonal elements and change the sign of the off diagonal elements. Okay, so that's your inverse. Okay, so now the transfer function is equal to C times SI minus A inverse times B, which is equal to C is equal to 3 and 1. SI minus A is this one here, which is equal to S plus 3 over S squared plus 3S plus 2, 1 over S squared plus 3S plus 2, and I have minus 2 over S squared plus 3S plus 2, and I have S over S squared plus 3S plus 2 times B, and B here is 0 and 1. Okay. 11. Okay, 12. What are we doing with time? Okay, we're almost finished. So if you do the multiplication, G of S is equal to 3 and 1 times 1 over S squared plus 3S plus 2, and S over S squared plus 3S over 2, which is equal to, if you do the multiplication here, you will end up with 3 plus S over S squared plus 3S plus 2. Okay, so of course this is what we expect, because how many inputs and how many outputs for this system does this system have? It has 1 input and 1 output, and that's what we would expect. Okay, we expect a scalar transfer function. Any question? All right, I think that will do it for today. Thank you very much, and see you on Thursday.
Thank you.
Thank you. Bye-bye.